The night sky above Ukraine holds its breath on August 30th, 2019. At the Crimean Astrophysical Observatory, automated telescopes sweep methodically across predetermined coordinates, their digital sensors collecting photons that have traveled unimaginable distances. The ATLAS survey system, Asteroid Terrestrial Impact Last Alert System, performs its quiet vigil, scanning for objects that might threaten Earth. Tonight, like countless nights before, the telescope captures thousands of points of light, each one catalogued, measured, cross-referenced against previous observations that stretch back decades. The observatory sits beneath a dome of stars that have witnessed the rise and fall of civilizations, the formation of planets, the birth and death of suns. Yet, tonight, among all these ancient lights, one particular photon carries information that will reshape humanity's understanding of what travels between stellar systems. This photon began its journey from a surface illuminated not by our sun, but by the reflected light of a star whose name appears in no human catalogue, whose existence remains unknown to terrestrial science. Among these countless stellar whispers, one dot appears unremarkable. Its brightness registers at magnitude 19, 6, so faint that the human eye could never perceive it, even through the largest amateur telescopes. The object moves against the background stars at a rate suggesting it belongs to our solar system, perhaps another asteroid wandering the space between Mars and Jupiter. The automated systems assign it a preliminary designation A2019Q4. The A indicates an asteroid. The numbers mark the year and discovery period. Nothing in this moment suggests that this single point of light will soon force astronomers to question fundamental assumptions about matter, motion, and the nature of objects that drift through interstellar space. The discovery image shows only a streak, the object's motion during the 30-second exposure, creating a thin line against the stellar backdrop. This motion speaks of orbital mechanics, of gravitational relationships with our sun that stretch back billions of years to the solar system's formation. Yet something in the mathematics whispers differently. The streak's length and orientation hint at velocities that don't quite match the expected patterns for objects born within our star's gravitational influence. The preliminary orbital calculations suggest an unusually high eccentricity, the kind that marks objects arriving from the solar system's distant edges, the Kuiper belt, the scattered disk, perhaps even the theoretical Oort cloud where comets wait in frozen suspension. In the following days, additional observations accumulate like layers of sediment in an archaeological dig. Each measurement refines the object's position, its apparent motion across the sky, the subtle variations in its brightness. The International Astronomical Union's Minor Planet Center collects these reports from observatories across 6 continents, feeding them into orbital determination algorithms that have successfully tracked tens of thousands of asteroids and comets over decades of systematic observation. The calculations converge slowly, iterations revealing an increasingly strange trajectory that defies conventional categorization. This object approaches the Sun not in the familiar elliptical paths of solar system natives, but along a hyperbolic curve, the mathematical signature of something that has never been gravitationally bound to our star. The orbital eccentricity exceeds unity, meaning the visitor follows an open-ended path that will carry it back into interstellar space after its brief encounter with our solar system's warmth. Only twice before has humanity confirmed such a trajectory. Oumuamua in 2017 and Tuuyue Borisov in 2019. Now a third interstellar wanderer announces its presence through the patient accumulation of photometric data points. The realization settles quietly over the astronomical community like morning mist. This visitor originated beyond the gravitational influence of our Sun, somewhere in the vast darkness between stellar systems where temperatures hover just above absolute zero. Its journey to our solar system may have lasted millions of years, drifting through space so empty that individual atoms become rare encounters. The Discovery team applies for a new designation, and the object becomes 3O Atlas, the third interstellar visitor to receive official recognition from the international astronomical community. Yet even as telescopes around the world turn to examine this cosmic stranger, something else begins to unfold in the accumulating data. The object's brightness starts to increase in ways that asteroid models cannot explain. Simple thermal calculations predict how reflected sunlight should behave as the visitor approaches our star. But 3E Atlas defies these predictions with systematic stubbornness. Spectroscopic observations reveal absorption lines that speak of water and carbon compounds, materials that shouldn't be present on the surface of a simple rock that has spent eons traveling through space where temperatures would freeze these substances into solid ice. The mathematical models that successfully predict asteroid behavior begin to fail, one by one, as 3I Atlas refuses to conform to terrestrial expectations. Newton's laws of motion describe how objects should accelerate under gravitational influence, but this visitor shows subtle deviations that suggest additional forces at work. The brightness variations hint at a rotating body, but the periods don't remain constant like those of familiar asteroids. Instead, the light curves display complex patterns that speak of structural changes occurring on timescales measured in days rather than the billions of years typically required for geological processes. Night after night, the observations accumulate in digital archives that will outlast the civilizations that create them. Each measurement adds another piece to a puzzle that seems to grow more complex rather than resolving into clarity. Professional observatories coordinate observation schedules across time zones, ensuring continuous coverage as Earth's rotation carries different telescopes into darkness. Amateur astronomers contribute their own measurements, adding to the growing database with equipment that would have seemed impossibly sophisticated just decades ago. The object's motion deviates slightly from pure gravitational trajectories, as if some invisible force provides gentle acceleration. This non-gravitational acceleration resembles the rocket effect seen in comets, where sublimating ice creates jets that can alter orbital motion. But 3I Atlas displays this acceleration at distances from the Sun, where water ice should remain frozen solid, where temperatures barely exceed the background radiation left over from the universe's birth. The physics of sublimation cannot explain what drives this visitor's increasingly rapid motion through our solar system. Surface features appear and disappear in high-resolution imaging like mirages shimmering in desert heat. The object's apparent size changes in ways that suggest either extreme elongation or dramatic variations in reflectivity. Thermal infrared observations paint a picture of temperature distributions that don't match any known class of solar system object. The accumulated data begins to resemble not a single coherent picture, but a collection of contradictory evidence that challenges fundamental assumptions about how matter behaves in the cold depths of space. The international network of observers maintains its quiet vigil, recording the stranger's passage through our solar system with instruments sensitive enough to detect the heat signature of a campfire on the moon. Radio telescopes listen for any hint of artificial signals, finding only the natural emissions expected from heated rock and ice. Optical telescopes map the visitor's rotation and search for signs of fragmentation or outgassing. Infrared sensors measure thermal emissions that reveal internal temperatures and surface composition. In the data files that grow larger each night, 3Y Atlas begins its transformation from simple discovery to profound mystery. The numbers whisper of processes unknown, of behaviors that will force scientists to question whether their understanding of interstellar objects applies to visitors from stellar systems with different formation histories. Perhaps the physics that governs matter in our solar system doesn't extend uniformly to objects forged in the gravitational fields of alien suns, under radiation environments that Earth-based science has never encountered. Only later will researchers understand that this quiet detection on an August night in Ukraine marks the beginning of humanity's encounter with something that challenges every model of how interstellar visitors should behave. The stranger approaches, accelerating through space in ways that violate established theory, carrying within its mysterious behavior questions that will haunt astronomy for generations. The orbital calculations arrive like whispered confessions from the void itself. In observatories scattered across continents, astronomers feed the accumulated position measurements into software that has successfully tracked thousands of solar system objects for decades. The algorithms converge with mathematical certainty on parameters that should be impossible. 3I Atlas follows a hyperbolic trajectory with an eccentricity of 4, to a number that speaks of velocities so extreme they can only originate from beyond our sun's gravitational dominion. This eccentricity value exceeds that of Oumuamua by a factor of nearly 2, marking 3U Atlas as the most obviously interstellar object ever detected, where Oumuamua's hyperbolic excess velocity measured 26 kilometers per second, the speed it retained after escaping our sun's gravity. This new visitor approaches with energies that suggest an origin from stellar neighborhoods where different physical processes shape matter and motion. The numbers whisper of a journey that began perhaps millions of years ago, when 3I Atlas received its initial velocity from gravitational interactions near an alien star system. The orbital plane tilts at 17 degrees to the ecliptic, that fundamental reference frame defined by Earth's path around the Sun. This inclination places the visitor's trajectory well outside the flattened disk, where planets and most asteroids maintain their orderly processions. Instead, 3I Atlas approaches from the direction of the constellation Draco, diving toward our solar system's heart along a path that intersects the orbital planes of multiple worlds. The geometry speaks of origins utterly disconnected from the processes that shaped our familiar solar system architecture. Astronomers calculate the visitor's closest approach to the Sun, perihelion, will occur at a distance of 37 million kilometers, well inside Mercury's orbit, but safely beyond the solar corona's superheated plasma. At this distance, solar radiation will heat the object's surface to temperatures exceeding 500 Kelvin, hot enough to sublimate water ice and drive off volatile compounds that might cling to its surface. The thermal calculations predict a brightening event as reflected sunlight increases and outgassing begins. Yet the magnitude of brightening already observed suggests processes far more complex than simple illumination geometry. The velocity vectors tell their own story of cosmic exile. At its current distance from the Sun, 3I Atlas moves at approximately 42 kilometers per second relative to our star, a speed that dwarfs the orbital velocities of familiar planets. Earth circles the Sun at a leisurely 30 kilometers per second, while even Mercury, racing through its close solar orbit, manages only 47 kilometers per second at perihelion. This interstellar visitor carries kinetic energies that speak of acceleration processes unknown in our quiet stellar neighborhood. Gravitational modeling reveals the visitor's future trajectory with mathematical precision. After its brief encounter with our solar system's inner regions, 3I Atlas will depart along a path that carries it toward the constellation Lynx, accelerating as our Sun's gravity assists its escape velocity. The hyperbolic orbit ensures this encounter remains temporary, a single pass through our cosmic neighborhood that will last mere months before the visitor returns to the interstellar medium from which it emerged. Yet the numbers also reveal troubling inconsistencies. The orbit shows systematic deviations from pure Keplerian motion, the mathematical description of how objects should move under gravitational influence alone. These deviations manifest as small but measurable accelerations that cannot be explained by the gravitational fields of any known solar system object. The visitor appears to generate its own propulsion, as if invisible jets push against the vacuum of space to alter its trajectory in subtle but persistent ways. The magnitude of these non-gravitational accelerations resembles those observed in comets, where sublimating ice creates reaction jets that can significantly alter orbital motion. But 3I Atlas displays this behavior at distances from the Sun where comet nuclei typically remain dormant, frozen into geological inactivity by the cold of deep space. The physics of sublimation cannot explain accelerations observed when the object travels beyond Jupiter's orbital distance, where solar heating remains insufficient to vaporize common ices. Thermal models struggle to reconcile the visitor's observed brightness with its calculated distance and size. The object reflects sunlight with an efficiency that suggests either an unusually bright surface composition or geometric properties that concentrate reflected light in Earth's direction. Standard asteroid models assume roughly spherical bodies with surface compositions similar to meteorites. But 3I Atla defies these assumptions with systematic persistence. Its brightness variations suggest either extreme elongation, perhaps 10 times longer than wide, or surface features that create dramatic albedo variations. The mathematical analysis reveals another troubling inconsistency in the visitor's rotation period. Initial observations suggested a rotation every 8.7 hours, typical for small asteroids that have achieved rotational equilibrium through billions of years of minor collisions. But subsequent measurements show variations in this period, as if the object's rotation accelerates and decelerates in response to internal processes or external forces that remain invisible to terrestrial instruments. Dynamical studies attempt to trace the visitor's origin through three-dimensional stellar motion models. The calculations work backward through time, accounting for the gravitational influence of nearby stars and the galaxy's overall rotation. The analysis suggests 3I Atlas originated from a stellar system located approximately 500 light-years from Earth, a distance so vast that the visitor's journey to our solar system required millions of years of drift through interstellar space where temperatures hover near absolute zero. The orbital geometry also reveals why this interstellar visitor remained undetected until its discovery in August 2019. The object approached from a direction nearly aligned with our solar system's motion through the galaxy, creating a slow, apparent motion against the background stars that automated survey systems initially classified as noise. Only when 3I Atlas began its acceleration toward the Sun did its motion become rapid enough to trigger detection algorithms designed to identify potentially hazardous asteroids. Each successive orbital calculation refines the visitor's parameters while deepening the fundamental mystery of its behavior. The mathematics describe an object that simultaneously conforms to and violates the basic principles of celestial mechanics. 3I Atlas follows a predictable trajectory shaped by solar gravity, yet displays accelerations that suggest additional forces operating according to unknown physical principles. The numbers accumulate like evidence in an unsolvable case, each measurement adding precision to parameters that describe increasingly impossible behavior. In conference rooms and research offices around the world, astronomers gather around computer screens displaying orbital plots that challenge decades of theoretical understanding. The visitor approaches our Sun along a path governed by mathematics that extend beyond current scientific knowledge, carrying within its trajectory questions that may outlast the civilizations attempting to answer them. The brightness measurements arrive each night like vital signs from a patient whose condition defies medical explanation. Across the globe, photometric systems record the steady strengthening of 3I Atlas as it drifts through the gravitational architecture of our solar system. What began as a faint smudge requiring the most sensitive digital cameras has brightened by nearly 2 magnitudes in just 6 weeks, an increase that transforms the visitor from invisible speck to detectable target for advanced amateur telescopes. The brightening follows no familiar pattern. Standard thermal models predict how reflected sunlight should increase as an object approaches our star, following inverse square laws that have governed astronomical brightness calculations for centuries. Yet 3I Atlas brightens faster than these models allow, as if additional light sources activate within its structure. The excess luminosity suggests processes beyond simple solar illumination, perhaps the sublimation of exotic ices or the exposure of highly reflective materials buried beneath a darker surface layer. Observatories coordinate their measurements through international networks that span 6 continents and multiple time zones. The Catalina Sky Survey in Arizona records brightness values each clear night, while telescopes in Chile, South Africa, and Australia maintain coverage as Earth's rotation carries different facilities into darkness. The accumulated photometry creates a continuous record of the visitor's approach, revealing brightness variations that occur on timescales ranging from hours to weeks. The short-term variations suggest rotation, as surface features with different reflectivities pass in and out of view. But these rotational signatures display troubling inconsistencies that challenge basic assumptions about solid body mechanics. The brightness peaks don't occur at regular intervals, instead showing systematic drift that implies either a changing rotation period or complex geometric effects that current models cannot accommodate. Some observations suggest the visitor rotates every 8.7 hours, while others indicate periods as short as 6.3 hours variations that would require impossible changes in angular momentum for a solid object. Spectroscopic analysis of the brightening light reveals molecular signatures that shouldn't exist on an asteroid's surface. Water vapor absorption lines appear in spectra taken when 3I Atlas remains well beyond Mars' orbit, where solar heating should be insufficient to sublimate ice deposits. The presence of OH radicals. Fragments of water molecules broken apart by solar radiation confirms that H2O molecules escape from the visitor's surface at temperatures far below the normal sublimation threshold. These water signatures intensify as weeks pass, suggesting increasing rates of molecular loss despite the visitor's continued distance from our Sun. The spectral lines display Doppler shifts that indicate expansion velocities of several hundred meters per second, fast enough for the escaping molecules to overcome the object's weak gravitational field and disperse into space. This molecular outflow creates a tenuous coma around 3I Atlas, invisible to optical telescopes, but detectable through careful spectroscopic analysis of absorbed sunlight. Carbon monoxide lines also appear in the spectra. Speaking of even more volatile materials escaping from the visitor's interior, these CO molecules require less solar heating to achieve sublimation. Yet their presence at such distances from the Sun suggests either unusually efficient heat transfer within the object's structure or internal energy sources that remain unidentified. The molecular outflow rates calculated from spectral line strengths indicate mass loss approaching several tons per day, a hemorrhaging of material that should be impossible for such a small object at its current solar distance. The brightening also displays color variations that hint at compositional changes occurring in real time. Photometric measurements through different optical filters reveal shifts in the visitor's overall spectral properties as it approaches the Sun, initially appearing slightly redder than typical asteroids. 3i Atlas gradually develops a more neutral color signature that suggests either the exposure of buried materials or chemical alterations occurring on its surface. These color changes correlate with the brightness increases in ways that challenge established models of asteroid behavior. Objects that brighten due to closer solar proximity typically maintain constant color signatures unless they experience catastrophic disruption. Yet, 3i Atlas displays systematic color evolution that implies ongoing surface processes, perhaps the sublimation of reddish organic compounds that expose more neutral rocky materials beneath. Thermal infrared observations reveal another layer of mystery in the visitor's brightening behavior. Measurements at wavelengths of 10 and 20 micrometers detect heat emission that exceeds predictions based on solar illumination alone. The thermal excess suggests either internal heat sources or surface properties that trap and re-radiate solar energy with unusual efficiency. Standard asteroid thermal models assume surfaces composed of rocky materials with well-characterized thermal properties. But 3i Atlas radiates heat like an object with fundamentally different composition. The infrared measurements also reveal temperature variations across the visitor's surface that change on timescales of hours. These thermal patterns don't correlate with the expected day-night temperature cycle for a rotating asteroid, instead showing complex distributions that suggest active heat sources or unusual thermal conductivity properties. Some surface regions appear significantly warmer than solar heating alone can explain, while others remain cooler than ambient space temperatures. Polarimetric measurements add yet another puzzling dimension to the brightening phenomenon. Light reflected from 3i Atlas shows polarization characteristics that change as the visitor approaches our Sun, suggesting either evolving surface texture or the activation of scattering processes unknown in conventional asteroid physics. The polarization signatures resemble those seen in comet Comets, yet the visitor displays these characteristics at distances where comet nuclei typically remain inactive. Radio telescopes detect faint emissions at centimeter wavelengths that correlate with the optical brightening events. These radio signals suggest electrical activity within or around the visitor, perhaps the ionization of escaping molecules by solar radiation or internal processes that generate electromagnetic fields. The radio emissions vary with the same periods as the optical brightness changes, implying a physical connection between the visitor's rotational state and its electromagnetic activity. Each night's observations add new data points to brightness curves that grow increasingly complex rather than converging towards simple explanations. The visitor's approach transforms from predictable astronomical event to ongoing mystery that challenges fundamental assumptions about how small bodies behave in interplanetary space. Professional astronomers share preliminary results through electronic circular networks, while amateur observers contribute their own measurements to collaborative databases that document the visitor's impossible behavior. The brightening continues with mechanical persistence, as if 3i Atlas operates according to physical laws that extend beyond terrestrial scientific understanding. In research offices and observatory control rooms, scientists gather around computer screens displaying light curves that violate decades of established theory. The visitor approaches our Sun while generating luminosity through processes that remain invisible to the most sophisticated instruments humanity can deploy. The starlight carries secrets encoded in wavelengths that telescopes pass like ancient texts written in languages nearly forgotten. Across the electromagnetic spectrum, 3i Atlas speaks through absorption lines that appear and disappear in spectral data collected by instruments sensitive enough to detect individual photons, arriving after journeys measured in astronomical units. Each wavelength tells part of a story that grows more complex with every observation, revealing molecular signatures that challenge fundamental assumptions about interstellar objects. The water vapor lines appear first, thin, dark bands etched into the continuous spectrum of reflected sunlight at wavelengths near 1.4 micrometers. These absorption features shouldn't exist at the visitor's current distance from our Sun, where temperatures remain too cold to sublimate water ice from exposed surfaces. Yet the spectral signatures strengthen night after night, indicating increasing quantities of H2O molecules surrounding the object in a tenuous atmosphere that extends thousands of kilometers into space. Hydroxyl radicals follow in the spectral record, their characteristic absorption at 0. 31 micrometers, marking the photodissociation of water molecules by solar ultraviolet radiation. These OH fragments form when water vapor encounters the Sun's energetic photons, breaking apart into component atoms that absorb light at specific wavelengths determined by quantum mechanical selection rules. The presence of hydroxyl signatures confirms that water sublimation occurs at rates approaching several hundred kilograms per hour, a molecular hemorrhaging that should drain any reasonable ice reserves within months. Carbon monoxide lines emerge in the near-infrared spectrum around 2.3 micrometers. Speaking of even more volatile materials escaping from the visitor's interior, these CO molecules require minimal solar heating to achieve gas phase, yet their abundance suggests reserves that exceed what surface deposits could provide. The spectral line profiles show Doppler broadening that indicates expansion velocities near 400 meters per second speeds that carry the escaping molecules well beyond the object's gravitational influence into the interplanetary medium. The molecular signatures display temporal variations that correlate with the visitor's rotational period, suggesting that outgassing occurs preferentially from specific surface regions. As 3I Atlas rotates, bringing different hemispheres into view, the spectral line strengths vary by factors of 2 or 3. This rotational modulation implies either compositional heterogeneity across the surface or geometric effects that concentrate molecular outflow in particular directions. The patterns repeat with clockwork precision every 8.7 hours, yet the phase relationships drift slowly over weeks of observation. Sodium D lines appear sporadically in high-resolution spectra taken when atmospheric conditions permit wavelength measurements accurate to parts per million. These atomic signatures at 589.0 and 589. 6 nanometers indicate the presence of metallic sodium in the escaping gas cloud, a component that suggests thermal processing of rocky materials at temperatures approaching 1000 Kelvin. Yet thermal models predict surface temperatures no higher than 200 Kelvin at the visitor's current solar distance, creating another impossible requirement for heat sources that remain unidentified. The spectroscopic measurements reveal isotopic ratios that differ significantly from solar system norms. Deuterium to hydrogen ratios in the water vapor appear enhanced by factors of 2 compared to terrestrial oceans, suggesting formation processes in interstellar environments where different nucleosynthetic pathways operate. These isotopic signatures carry the chemical fingerprints of stellar formation regions, unlike those that created our own solar system. Speaking of origins in galactic neighborhoods, where different physical conditions governed planetary accretion, carbon isotope ratios show similar anomalies, with carbon-13 abundances that exceed solar system values by measurable margins. These isotopic variations indicate that the carbon-bearing molecules escaping from 3A Atlas formed in stellar environments with neutron flux densities or temperature profiles that differ from those experienced by solar system materials during their initial condensation 4.5 billion years ago. The visitor carries within its molecular inventory the chemical signature of alien star formation processes. Organic spectral features appear intermittently in mid-infrared observations conducted during periods of exceptional atmospheric stability. Absorption bands near 3.4 micrometers suggest the presence of hydrocarbon molecules, possibly complex organic compounds that survived the visitor's journey through interstellar space, where cosmic ray bombardment should destroy such fragile chemical structures. The organic signatures remain weak and difficult to confirm, appearing at the limits of instrumental sensitivity like whispers from chemistry that operated under conditions unknown to terrestrial science. The Doppler shifts of spectral lines reveal the three-dimensional structure of the molecular outflow around 3I Atlas. Gas escaping from the sunward hemisphere shows blue-shifted absorption lines, indicating motion toward Earth as molecules accelerate away from the visitor's surface. The anti-solar hemisphere produces red-shifted signatures as escaping material moves away from terrestrial observers. These velocity patterns create a map of molecular motion that extends the visitor's effective size from its solid nucleus to a diffuse atmosphere spanning thousands of kilometers. High-resolution spectroscopy reveals fine structure in the molecular absorption lines that speaks of rotational and vibrational excitation states within the escaping gas. The population distributions among different energy levels indicate gas temperatures near 150 Kelvin, significantly warmer than the equilibrium temperature expected for molecules in interplanetary space. This thermal excess suggests that the escaping gas carries energy from internal heating processes or receives warming from sources other than direct solar illumination. Some spectral observations detect polarization signatures in scattered sunlight that indicate the presence of microscopic dust particles mixed with the molecular outflow. These polarization measurements suggest grain sizes in the micrometer range larger than typical interstellar dust, but smaller than particles expected from mechanical erosion of rocky surfaces. The dust production implies either sublimation-driven fragmentation of surface materials or the entrainment of pre-existing particles within the escaping gas flow. Temporal monitoring reveals that spectral line strengths vary on multiple timescales beyond the primary rotational period. Some molecular signatures show enhancements that last several hours, suggesting localized outgassing events or the activation of specific surface regions. Other variations occur over periods of days or weeks, implying evolutionary processes that alter the visitor's outgassing behavior as it approaches our Sun along its hyperbolic trajectory. The accumulated spectroscopic data creates a portrait of an object that operates according to physical processes unknown in solar system science. Each molecular signature adds evidence for chemical and thermal behavior that violates established theories of how small bodies should respond to solar heating. The visitor's spectrum carries information encoded in wavelengths that speak of origins in stellar systems where different formation processes created materials with properties that challenge terrestrial understanding. In spectroscopy laboratories around the world, researchers compare the 3I Atlas observations with databases containing hundreds of thousands of reference spectra from meteorites, comets, and asteroids. The visitor's molecular fingerprints match no known classification, instead requiring the creation of entirely new categories for objects that bridge the gap between interstellar chemistry and planetary science. The starlight filtered through 3I Atlas whispers of processes that extend beyond current scientific knowledge, carrying within its spectral signatures questions that may outlast the instruments attempting to decode them. The astrometric measurements arrive with the precision of atomic clocks, each data point marking 3I Atlas's position against the stellar background with accuracies measured in milliarc seconds. This positional astronomy, the ancient science of tracking celestial motion, now operates at technological limits that would have seemed impossible just decades ago. Satellite-based telescopes eliminate atmospheric turbulence, while ground-based interferometers combine light from multiple apertures to achieve angular resolutions that can distinguish features smaller than coins viewed from thousands of kilometers away. Yet these exquisite measurements reveal motion that violates the fundamental principles of celestial mechanics. 3I Atlas accelerates along its trajectory in ways that pure gravitational theory cannot explain, displaying systematic deviations from Keplerian orbital motion that accumulate over weeks of observation. The visitor moves faster than calculations predict, as if invisible forces supplement the sun's gravitational attraction with additional acceleration directed along the object's velocity vector. The magnitude of this non-gravitational acceleration measures approximately 4.8 x 10⁻⁶ meters per second, squared, a seemingly negligible value that represents roughly 1/10,000,000th of Earth's surface gravity. Yet this minute force, applied continuously over the months of the visitor's passage through our solar system, produces cumulative positional changes that exceed measurement uncertainties by factors of 10 or more. The effect manifests as a systematic leading of the object's predicted position, as if 3I Atlas runs slightly ahead of schedule in its appointment with perihelion. This acceleration resembles the non-gravitational forces observed in comets, where sublimating ice creates reaction jets that can significantly alter orbital motion. The rocket effect occurs when molecules escaping from a comet's surface carry away momentum, creating thrust that supplements or opposes the gravitational forces governing the nucleus's trajectory. But 3 Atlas displays this acceleration at distances from the Sun where comet nuclei typically remain frozen into inactivity, where solar heating should be insufficient to drive significant sublimation of water ice or other common volatiles. The acceleration vector analysis reveals the forces act primarily in the radial direction away from the Sun, with smaller components along the orbital velocity vector. This geometry suggests that whatever process drives the acceleration operates most efficiently on the visitor's sunward hemisphere, where solar illumination reaches maximum intensity. Yet thermal calculations indicate that even at maximum solar heating, surface temperatures should remain below the sublimation threshold for water ice, the most abundant volatile compound expected in objects formed beyond the solar system's snowline. Sophisticated orbital fitting procedures attempt to reconcile the observed motion with theoretical predictions by introducing additional force terms into the equations of motion. These models treat the non-gravitational acceleration as a parameter to be determined from the astrometric data, allowing the mathematical framework to accommodate forces beyond pure gravity. The best fit solutions require accelerations that vary with distance from the Sun according to power laws that don't match any known physical process. The temporal evolution of the acceleration presents another puzzle that challenges conventional understanding. Rather than remaining constant or varying smoothly with solar distance, the non-gravitational forces display fluctuations that occur on timescales of days to weeks. These variations correlate weakly with the visitor's rotational period, suggesting connections between the acceleration magnitude and which hemisphere faces toward the Sun. Yet the correlations remain imperfect, as if additional factors influence the force generation beyond simple geometric considerations. Some acceleration episodes appear to occur independently of the visitor's orientation relative to the Sun, implying either internal energy sources or interactions with the solar wind that operate according to unknown physical principles. These episodes manifest as brief periods of enhanced acceleration that last several days before returning to baseline levels. The trigger mechanisms for these events remain unidentified, occurring without obvious correlation to solar activity, magnetic field changes, or other measurable environmental factors. The precision astrometry also reveals that 3I Atlas experiences torques that alter its rotational state over observable timescales. The visitor's spin period varies by small but measurable amounts, sometimes shortening by minutes per rotation cycle, before gradually returning toward baseline values. These rotational changes suggest that whatever forces accelerate the object's center of mass also apply torques that modify its angular momentum in ways that solid body mechanics cannot explain. Gravitational modeling attempts to account for the acceleration by invoking previously unknown solar system mass concentrations or modifications to general relativity in the weak field limit. These theoretical exercises explore whether dark matter distributions, modified Newtonian dynamics, or exotic gravitational effects might explain the observed motion without requiring non-gravitational forces. However, the required mass distributions or gravitational modifications would produce observable effects on other solar system objects that remain undetected despite decades of high-precision orbital monitoring. The possibility of systematic measurement errors receives careful investigation as teams of astronomers cross-check their astrometric reductions and calibration procedures. Independent observations from different telescopes and analysis pipelines confirm the reality of the anomalous acceleration, eliminating instrumental artifacts or data processing errors as potential explanations. The visitor's motion deviates from gravitational predictions with statistical significance that exceeds 20 standard deviations, a certainty level that leaves little room for measurement uncertainty. Radio interferometry provides additional confirmation of the acceleration through observations at wavelengths immune to optical atmospheric effects, very long. Baseline interferometry arrays track 3I Atlas by detecting faint thermal emissions from its heated surface, achieving positional accuracies that rival or exceed optical measurements. These radio observations confirm the systematic positional deviations, providing independent verification that the acceleration represents real physical motion rather than observational artifact. The acceleration magnitude shows weak but measurable dependence on the visitor's heliocentric distance, following approximately an inverse square relationship similar to solar illumination intensity. This correlation suggests that solar energy input drives whatever process generates the non-gravitational forces, yet the required coupling efficiency between absorbed solar radiation and mechanical thrust exceeds theoretical predictions by orders of magnitude. The visitor converts solar energy into directed momentum with an efficiency that challenges fundamental principles of thermodynamics and radiation pressure physics. Attempts to model the acceleration using conventional outgassing physics require mass loss rates that would deplete any reasonable volatile reserves within months of solar approach. Yet spectroscopic observations detect molecular outflow rates several orders of magnitude smaller than those needed to explain the observed thrust. This discrepancy between required and observed outgassing creates another impossible requirement for physical processes that operate with efficiencies unknown in solar system science. The accumulated astrometric evidence paints a portrait of an object that moves according to forces beyond current scientific understanding. Each measurement adds precision to parameters that describe increasingly impossible motion, as if 3I Atlas operates according to physical laws that extend beyond terrestrial knowledge. The visitor accelerates through space with mechanical persistence, carrying within its trajectory questions about the fundamental nature of matter, motion, and the forces that govern objects traveling between the stars. The outgassing phenomenon unfolds like a slow chemical reaction occurring in the vacuum laboratory of space itself. Across multiple wavelengths and observational techniques, instruments detect the steady release of molecular species from 3I Atlas